In analysing this and similar circuits, we will use a phasor diagram that includes the voltage and current phasors for each of the components. Here, because of KVL rule, Kirchhoff's voltage loop rule, the instantaneous total voltage across all three components is equal to the source voltage at that instant, and its phasor is the vector sum of the phasors for the individual voltages. The complete phasor diagram for this circuit is shown here. This may appear complex, but it is not as bad as it looks. I'm going to explain it in steps. The instantaneous current I has the same value at all points of the circuit. Thus, a single phasor I of length proportional to the current amplitude represents the current in each circuit element. Let us use the symbols VR, so we're going to use these symbols, VR, which is VAC, and VL, which is VCD, so that's the voltage across the inductor. VR is the voltage across the resistor, and little VDB is the voltage across the capacitor. So let us use the symbols VR, VL and VC for the instantaneous voltages across R, L and C, and VR, VL and VC for their maximum values. We denote the instantaneous and maximum source voltages by lowercase v and capital V. We have just shown that the potential difference between the terminals of a resistor is in phase with the current in the resistor, and that its maximum value equals I times R. Thus the phasor VR is in phase with the current vector and represents the voltage across the resistor. Its projection on the horizontal axis at any instant gives the instantaneous potential difference VR. We drop the vertical down, and that gives us, as that rotates round, always it's that component that is the length we're dealing with. That's the instantaneous voltage across the component. The voltage across the inductor here, which is this value here, we're writing that as IXL. That voltage there leads VR, you can see, by 90 degrees. The phasor VL represents the voltage across the inductor, and its projection at any instant on the horizontal axis equals lowercase VL. So looking at this one here, I've just drawn that out again. Again, you can see, look, there's the component of the instantaneous voltage across the inductor at any time is given by dropping a horizontal from this rotating phasor. We drop the horizontal one, that gives us the instantaneous value. Voltage across a capacitor lags the current by 90. So the capacitor here, you can see it lags the current, so it's 90 degrees behind it. You can see that's 90 degrees behind it, so we draw that there. Inductor and the capacitor's voltages are always opposite and parallel. The voltage amplitude is given by VCIXC, which we've written here. The phasor, VC, represents the voltage across the capacitor, and its projection at any instant onto the horizontal axis equals lowercase VC. So again, this VC rotating round, and if we drop a horizontal on the x-axis here, we'll get the instantaneous voltage across the capacitor. Looking at VAB, so that the voltage across this whole lot between terminals A and B equals at every instant the algebraic sum of the potential differences lowercase VR, lowercase VL and lowercase VC for the instantaneous voltages. That is, it equals the sum of the projections of the phasors capital VR, capital VL and capital VC. But the projection of the vector sum of these phasors is equal to the sum of their projections. So the vector sum, so the final vector sum, this V here, must be the phasor that represents the source voltage. To form the vector sum, we first subtract the phasor VC, capital VC, from the phasor capital VL. Since these always lie along a straight line, so we subtract these two here, giving the phasor VL minus VC. That will give us our final component in that direction. And you can just like project that over to here, because you see that they're parallel lines. So obviously we can think of this as a right angle triangle now. So we've got the magnitude of V on this side, and we've got the magnitude of VL minus VC on this side, and then we've got the magnitude of the total voltage on that side. So that's Pythag, yes? V squared equals that all squared plus VR squared. And I've written that here. So we got the VAB, the voltage across AB, is equal to the square root of VR squared add VL plus VC all squared. And you know that those components can be written as IR, I is the constant again, it's the same throughout the circuit, remember, and VLVC is IXL, which is the reactance term, this is the resistance term, minus IXC, because remember the voltage across the capacitance can be written as I reactance, and for the inductor it's I the reactance of an inductor. So we can rewrite that like that, and then of course we could bring the I outside like so, and then we've got this equation. Now it's all in terms of ohms now. So we've got R squared, and this is in terms of ohms, that's in terms of ohms. This part inside here, XL minus XC, is called the reactance of the circuit. So that's the total reactance, because that's not a reactive component. These are reactive. In other words, these are components that will store energy, whereas the resistor will burn energy. But those two components won't. They will just react. They'll store or they'll put energy back into the circuit. Combined like that, this is called the reactance of the circuit, and you sometimes see that as capital X. Finally, we define the impedance Z of the circuit as Z equals R squared XL minus XC all squared, square root of, with a capital X there, we can just write square root of R squared plus capital X squared, remembering that X is equal to this. Impedance Z plays the same role as resistance R in a DC circuit. Note, however, that the impedance is actually a function of this impedance is actually a function of R, L and C, as well as of the frequency omega W. The complete expression for impedance Z for a series circuit is then, if you replace the X with the reactance terms, and we know that XL is in fact omega times the inductance, and XC is in fact 1 over WC. So to write this down in terms of all of those components, L, C, W, we can write the impedance like this. Impedance here very clearly is dependent on the R, the frequency, the angular frequency, the inductance of the inductor, and the capacitance of the capacitor. The expression for the impedance Z of, say, A, an RL series circuit, or B, an RC series circuit, or C, an LC circuit, can be obtained from this equation by letting, for A, let XL equal 0, so you let XL equal 0. This then is the form of an RLC circuit. When we let, for B, XL, oh sorry, that was XC equals 0 for an RL series circuit. When we let B, XL equals 0, then we're going to get an RC series circuit. And finally for C, if we let R equals 0, we get an LC circuit. So this is quite general for all those different types of circuits, RL, RC and LC. So that's good, because we've only got to remember this one equation. The angle between the source voltage and the current, which we've labelled phi, is the phase angle of the source voltage V with respect to the current I. And we know this size here, which is VL minus VC. We know this magnitude here, which is VR. Then you can use tan theta, opposite divided by adjacent. So with that, we can find this angle between the source voltage and the current. If we know what the reactance of an inductor is and the reactance of the capacitor, we can plug those in. We know what the current, they cancel anyway in this case. And it just turns out that the angle, the tan of the angle there is in fact equal to X over R. So that's kind of cool. So to find the angle, we just take the inverse tan of that. So we can actually find how much the voltage is leading the current in this case just by measuring the total reactance over the R and taking the inverse tan of that. Hence, for example, if the current was represented by a cosine function, so let's say we represent the current by a cosine function. Now, we're going to represent the current by a cosine function, that's fine. So we can say I equals capital I cosine WT. The source voltage, we know, leads the current by an angle phi between 0 and 90, and its equation then is this. So in this diagram here, I've basically drawn the current here, and look, the voltage is leading. We can see the voltage is leading by phi. Now, if we drop that down, that's simply capital I cosine WT. For this one, we've dropped that down, that's VAB. Now, VAB now, in this case, you can see you've got to go WT, and then you've got to go this extra angle, yeah? So this cosine is going to be cosine WT add phi, yeah? So that's a good example. Now, of course, you could write it down differently. You could write it down as the voltage V is capital V cosine WT. So this time we're doing it in this way. So we're saying VAB is V cosine WT. Now we have to draw this angle. We have to say that WT is from here all the way up to here. Okay, so I've drawn it all the way up. So that means we know here that the current here is behind the voltage, yeah? So we know that that's lagging, yeah? So to get this angle, which is that angle to there, we've got to go all the way to WT, and then we've got to subtract. We're going to come back and subtract to get us back here. So if we use cosine for that as well, that's simply WT minus theta. I've shown it again here in the sense that this time I've set that VL is smaller than VC. So in this case, we've got this component we've got to work with. If we want to relate the voltage and the current with the cosine function, then obviously we can write the I term down as I cosine WT. WT is the angle from here all the way round to the I, yeah? So we can see that the voltage is lagging, is behind the current here. To get that, then we've got to go all the way up to there and back again. So we've got to go all the way to this angle, which is WT, and then back phi to get here. So it's WT minus phi. So you can see how that's come about. The phase angle is a nice way of representing all the behaviour of these three components in a circuit. It's very useful. So this analysis describes the steady state condition of a circuit, the condition that prevails after the circuit has been connected to the source for a long time. When the source is first connected, there may be additional voltages and currents called transients, whose nature depends on the time in the cycle when the circuit is initially completed. A detailed analysis of transients is beyond this intro set of lectures, but they always die out after a sufficiently long time, which could, in this case, we're talking a few milliseconds or something. Therefore, do not affect the steady state behaviour of the circuits.